All right, so maybe we can begin now.
Okay.
Okay, so I'll just briefly introduce you to the audience. Okay, so hello everyone. Today's speaker is Dr. Sudipto. So I'll just briefly introduce him before he begins presenting his interesting work. He's a postdoctoral research fellow at the INOCNR BEC Center of the University of Trento in Italy. He did his PhD from HRI in quantum information theory and computation under the supervision of Professor Ujjwal Sen. And then he moved to South Korea and then moved to Spain. And his research is mainly focused on problems in two main areas: quantum information theory and computation, and the interface of quantum information theory and quantum many-body physics. So, Dr. Sudip.
Okay. So, hello everyone. So, first of all, I'd like to thank Siddhasta for the invitation and giving me this opportunity to present my research work here. And here is the title of today's presentation: Linked Representation of Entanglement Entropy. And it will be based on these works which we have completed in recent years. But before going into the main discussion of today's talk, let me very quickly mention about my research areas. So I'm a theorist working in the field of quantum information theory and quantum computation. And I also work in the interface of quantum information theory and quantum many-body systems. So today, the topic that I'm going to present that actually falls in this category, that is the interface of quantum information theory and quantum many-body systems. So today, the main aim will be characterization of quantum entanglement in quantum many-body systems. And that we are going to do following a formalism that I'm going to introduce, which is known as linked representation of entanglement entropy. But before going into the main part of today's topic, or before going to know this, what exactly is this formalism, let me give you a very quick recap of the fact that why the people from quantum information and computation background are interested in studying quantum many-body systems in the first place. So we can divide this reason into broad part. So one reason is that, as we know that in past few decades, apart from many interesting theoretical developments, the field of quantum information theory and quantum computation has witnessed many interesting and significant experimental developments as well. So in this case, what we ask is that what should be the physical models, or what should be the physical system in which the schemes or the protocols of quantum computation or quantum information theory can be implemented faithfully with good amount of faithfulness. So in this regard, people have found that these quantum many-body systems are considered to be one such platform which are suitable for implementation of different quantum computation as well as information theoretic based protocols. So there are many reasons. So one such is that quite often they are scalable, and in many cases they provide good amount of protection against decoherence or environmental perturbation, as well as they can be implemented in a real experimental setup with high precision. So this is one of the reasons. And the other reasons, which is also equally interesting, is also developed parallelly, is the use of tools from quantum information theory to other branches of physics, in particular condensed matter systems or quantum many-body systems. So as we know that in quantum many-body systems, it's the common practice. We can have many exotic quantum phases in which are commonly distinguished or characterized using some conventional order parameters. So these order parameters help us to characterize the phases or identify different quantum phase transition points of the model. But in past years, people have also observed that, like as the conventional order parameter that we use in quantum many-body systems or condensed matter theory, quantum entanglement can also, in many cases, do the same job. Okay, so in other words, quantum entanglement can also be used for efficient or faithful characterization of different quantum many-body phases or detection of quantum phase transition points. Not only that, like as the conventional order parameter, in many cases, entanglement also exhibits scaling behavior. So it has finite scaling exponents. And there could be cases where entanglement can provide a better insights than the conventional order parameters. For example, in many cases, the study of entanglement properties can help us in characterize these topological phases, which are hard to characterize or distinguish using the conventional order parameters, in particular if the order parameters are local. So this is kind of, I can say it's a brief overview of why the people from our community are also interested in exploring different quantum many-body systems. But whatever be your motivation, the first thing one needs to start with is the characterization of quantum entanglement in quantum many-body system. So we need to see that how, if we have a quantum many-body system, so then how different parts of this quantum many-body systems are talking to each other, or how they are correlated with each other, how they are entangled with each other. And in this regard, a common practice is to analyze or see the scaling behavior of quantum entanglement in quantum many-body systems. So we need to understand these things. So what exactly is these things? Because this will be helpful to introduce the main part of this talk. So to introduce this concept, I will start with a lattice structure, and without loss of generality, here I'm considering a one-dimensional system. So it is a one-dimensional chain, and it could be periodic or open. And let's consider that we have n number of lattice sites, and at each lattice sites, we have one quantum particle. So the quantum particle we are starting with is also n. Now what we do next, we now divide this system in two parts. So we call one part as x, which consists of L number of sites or L number of quantum particles. And the remaining part is called as x complement, which consists the rest of the particles. That means n minus L number of particles. So what we do now is that we now try to see that if we now keep increasing the size of this left block step by step, then how the entanglement between these blocks x and x complement is going to behave. Okay. So in other words, we'll be looking at the scaling behavior of the entanglement between this block x and x complement as we keep on increasing the size of this block L. So we need a quantifier or a measure of entanglement that would estimate the amount of entanglement between these blocks. So one popular measure of quantum entanglement that we are considering is entanglement entropy. So which is a measure of quantum entanglement for pure quantum states and can be mathematically expressed like this. SL is minus trace of rho L, Ln rho L. And this rho L is the quantum state characterizing this part or the reduced part X only, consistent of Now, how to get this reduced density matrix rho L? So in order to get this reduced density matrix, we have to start with the full many-body state. That means the pure quantum state consisting of n number of sites. And from there, we have to trace out the degrees of freedom, which are not part of this block X, or rather part of this block X complement. So if we do this partial tracing operation, then we will end up with this reduced density matrix characterizing this block X only. And once we plug that to this equation, then we are going to get a number. So for instance, if SL is 0, then we have to understand that there is no entanglement between this block X and X complement. Similarly, any non-zero value of this measure SL would imply there is a finite amount of entanglement between the blocks X and X complement. So we now know how to compute the entanglement if I give you a quantum many-body state. So let me recap that what is our goal. So we have this quantum many-body state, and now we want to see the scaling behavior of the entanglement in this system as we increase the size of this left block X. So in other words, we are looking for the profile of this SL versus L plot. So people have observed that if we consider one-dimensional system and consider the ground state or the quantum states which are very close to the ground state, that means the low energy states, then the behavior of this SL versus L plot looks like this. So there could be some initial growth, and after a certain length, entanglement entropy saturates. In other words, the amount of entanglement between this block X and X complement no longer cares how many particles are there inside the block X. So this behavior is known as areal of feature of entanglement entropy. So I will come to that, why we are calling it as an areal by this term. But before that, let me give you another example, which is for two-dimension system. So like as before, if we now consider a two-dimension system, and similar to the 1D case, if we divide this in two parts, let's say x and x complement, and do the same analysis, that means if we try to see how the entanglement between these two blocks behaves, if we keep on increasing the size of this block x, then if it happens that here the entanglement remains proportional to L, where L is basically this white shaded region, that means the length of this region that is separating the block x from the x complement. So if we find the behavior like this, then we are going to call it, this is an area law feature for two-dimensional system. So we can keep going on like this and consider a lattice with higher dimension. So this will give us a mathematical formula, a general formula for the area law feature for any d-dimensional lattice. So for any d-dimensional lattice, this area law feature can be mathematically expressed like this. If you find that the entanglement entropy between any part of the system and its complement scales like this, that means it remains proportional to the length of the L to the power d minus 1, whereas the L is the length of the boundary that is separating the considered block from its complement, then we are going to say that for that lattice geometry, we are having an area law feature. Now let me come to the point that why we are calling it's an area law. So as we know that if we have a lattice with dimension d and the geometry with length L, then the volume is basically L to the power t. So what will be the area? So area is L to the power t minus 1. So that's why we are calling it an area law feature of quantum entanglement. Now, is this behavior generic? Okay, or are there any conditions that needs to be satisfied in order to have this kind of bounded growth of entanglement? So we have partial answer to that. So if you are dealing with one-dimensional system, then Matthew Hastings has proved that if the quantum Hamiltonian that you have is local, that means if you decompose the Hamiltonian, then you will find that this Hij term that consists of product of only some local operators. And if you also find that the spectrum of this Hamiltonian has a gap, that means the low energy states are well separated from the excited states, then one can show that in those cases, we should expect the area law feature for the ground state or the states which are very close to the ground state. But this exact proof holds only for one-dimensional system. For two-dimensional, we don't have any concrete proof. But people have reported that in two-dimensional or even higher dimension, there are plenty of examples where one can have this area law feature. Now, what is the message you are getting from this area law feature? If somebody says you that, okay, the physical system that you are considering exhibits this area law, then what is the insight you can get about the entanglement distribution in the system? So if you find that for your system, you have this area law feature, then you have to understand that the entanglement structure in the system is basically short-ranged. So the particles are entangled with each other provided they are sitting very near, close to each other. Okay, so there is no long-range entanglement in the system. So then how to understand this area law behavior? So consider we have this, again, we are back with this structure and we want to compute the entanglement entropy across this bipartition. So a short-range entanglement means that if we compute the entanglement across this bipartition, then a particle which is sitting, let's say, rightmost or the leftmost, that would not contribute to this entanglement entropy. Because those particles would remain entangled with its counterpart, which are sitting in the same block. Okay. So the main contribution of entanglement comes from the pair of particles which are sitting near the boundaries. Okay, for example, maybe the closest one or the sites which are just one side away from the boundary. So we know that how many such pair, now the question is how many such pair we can have for a fixed lattice geometry. So this is basically fixed by the area of the geometry. So we know that in 1D, the number is 1D, it's a constant. In 2D, we have it's proportional to the length of this boundary, and in 3D, it's L square, like that. So that's why the entanglement entropy also remains proportional to the area of the considered geometry. But why we are giving so much importance to this area law feature? So of course, it's a fundamentally very interesting, but it has a very important application as well. So in general, if we try to find out the low energy states of a generic quantum mini-body system, that's a very challenging task. So why so? So how you are going to do that? So in most of the cases, you need to rely on numerical techniques, because there will be only a few cases where you can proceed analytically. So you have to somehow rely on numerics. You have to do some optimization to find out the low energy states or the ground state of the model. Now, in general, such numerical techniques involves optimization over a large number of parameters. So let me give you an estimate. So let's say we have a quantum mini-body state consisting of n number of sites, and it can be, it's represented in some local basis. So a faithful representation of this state in this basis demands that we know all this C coefficient completely. And this C coefficient can be in principle real, imaginary, anything. So how many such C coefficient one can have for a system with n number of particles? And if we consider the dimension of the local Hilbert space is P, for example, P2 is qubit, P3 is qubit, and so on, then the number of such C coefficient we need to know for an efficient representation of this state in this basis is basically P to the power n. So you see that the number of coefficient increases exponentially with the size of system. As a result, this will restrict us to access the quantum state for large lattice sites, because our total memory is constant, so we cannot go up to very large system size. And this will also restrict us to study many interesting properties of the system. As we know that in many cases, we can get some insight about the system by studying or analyzing the scaling property of different quantum measure or different quantum properties. But those kind of scaling properties, that means the behavior of physical quantities in thermodynamic limit or close to thermodynamic limit, cannot be performed here. So this is a practical limitation. But if we find that the system obeys this area law feature, the system you are dealing with obeys this area law feature, then in that case, we can get tremendous advantage. So one can show that in that case, we do not need all such P to the power n coefficient for an efficient representation of the given quantum state in a generic basis. So rather, a very small number of parameters will be enough. Okay. So that's why we are giving the area law so much importance. And this would mean that you can, in those cases, you can access physical system up to a large number of lattice sites. So this is basically the underlying theory of this flourishing area of research called this tensor network theory. So this tensor network theory is a family of numerical, consists of numerical techniques which are very efficient and relies on this area law property and helps us to get the quantum states of physical system or low energy states of the physical system up to very large lattice size. So we have many members in this family. For example, we have the oldest member, density matrix normalization group or DMRG. We have matrix product state formalism for 1D. We have PEPs or projected entanglement pair states for 2D and many more. So if you want, if you can take a look at this reviews, which for an introduction of these things. So I hope I could able to convey the main message of this importance of this area law. Now, in our case, we are trying to provide a more generalized version of this area law feature. Now, what is generalized here? So to understand this thing, we first have to see that the notion of area law that I have introduced just now, that can actually be a path-dependent phenomenon. So how to see that? So for that, I will start with a quantum system, which is or a quantum quantum Hamiltonian known as this rainbow Hamiltonian. So it's a free harmonic Hamiltonian. That means there is no interaction in the system. But the coupling between the sides are not constant. Rather, it is modulated by this exponential factor. Now, when we take this parameter h to be very large, then the ground state of this model looks like this. So if you forget the Hamiltonian, you don't need to remember the Hamiltonian. So you can consider this ground state simply as a product of some concentric dimers or singlets. So these bonds are basically, there are Bell states you can consider. Okay. So this state has a very simple structure, as you can see. Now, what would be the scaling property of this state? So to analyze the scaling property, we have to apply the recipe that I have mentioned you a few slides before. So we have to start with, let's say, this structure that where we divide the system in two parts. We call one part as X and other as X complement, like we did before. And the task would be then to find out the entanglement entropy for this state as we keep on increasing the size of this left block step by step. Now, what would be the entanglement for this initial structure? Because this is the initial structure one need to start with. So here, the amount of entanglement entropy for this configuration would be nothing but the cost of breaking this one Bell state or this bond. Okay. Now, if we if we increase the size of this left block by one more unit, then you see for this configuration, we now need to break two bonds to separate this block 1, 2 from the rest of the system. So this will be the estimation of the amount of entanglement entropy. So the amount of entanglement entropy for this configuration has been doubled from the previous one. So if you keep doing this, then you see each time you are increasing the size of this left block by 1 unit, you are basically breaking one additional bond. So in this case, if you again plot this SL versus L graph, then instead of this saturation that I have mentioned, here you can see the entanglement entropy increases linearly with the size of the system. This is called as volume law. So you can see this is way far from the, far more. It's an extreme example of the deviation of the scaling of entanglement entropy from the area law. So that's why we are calling it as a volume law. But if we consider now the same system and try to look at this behavior from a different path, for example, let's now do a reshuffling or folding and try to see the system along this path where the system 1 is nearest to 2, 2 is nearest to n-1, 3 is nearest to n-2, and again repeat the same analysis. Then you are going to see that across this path, the system has bounded growth of entanglement or a perfect area. So how to see this? So again, we are starting with this same configuration. So what would be the entanglement for this configuration? So as we have mentioned that the amount of entanglement would be nothing but the cost of breaking one bond. So here you can see we need to break only one bond for this configuration. But if I now increase the size of this block, left block by 1 unit, so here you can see that I don't need to break any bond at all. In other words, for this configuration, the amount of entanglement entropy or amount of entanglement between the left and the right block is basically 0. And these are the only two options you can have. If you repeat this thing, so you only get this, either it is breaking one bond or it is not breaking any bond at all. So this is an example of a strict area law feature. So in this case, you don't even have this initial growth. So starting from beginning, it's saturated. So this simple example shows you that for a given quantum state, if you look at the system across one path where you have the volume law, then you may miss the area law feature. And this is because you are not looking at the system across the right path or across the path along which the system has this bounded growth. But this is a very simple example. To find this path of area law, you don't need to apply any techniques because I have not introduced it at all. But what would be the situation if I give you a generic quantum many-body system? So if I give you a generic quantum many-body system, let's say consisting of n number of sites, then the first question is that can we find a path for which we can recover a bounded growth of entanglement entropy or bounded growth of entanglement? And if it is that, what exactly is that path? Okay. So here comes our formalism. So this link representation formalism actually addresses this question. So this is basically the next thing we are going to see. So in the upcoming slides, I will introduce this formalism and then talk about its application and also the cases where we will see deviation from this link representation formalism. So let us try to understand this formalism slowly. So to introduce this formalism, I will again start with the quantum many-body state, let's say. But now I don't care about the history of this state, so I can get it from any physical model, or it can be as well as synthetic quantum state. Now, the statement of the link representation answer is following. So if we compute the entanglement entropy of any bipartition of this given quantum many-body state, so we are saying that that can be approximated as the sum of certain link strength connecting internal and external sides. So what do we mean by that? So to explain this statement, I will again take help of this schematic. So this is similar to the one where we divided the system in x and x complement. So you can just consider instead of x and x complement, here I'm using a and a bar. So the aim is to compute the entanglement entropy across this a and a bar of this quantum system or this quantum many-body state. So what we are saying is that that is basically can be done by just breaking the bonds, these Jij bonds, which are connecting the sides those belong to A to the sides those belong to A complement or A bar. So these bonds are weighted, so they have the value. So if you find the value of this, first you have to identify that what are the bonds which are connecting these blocks, and then you have to also find the values. And when you add up the values, that is going to give us an approximate value of the entanglement entropy or estimation of the entanglement entropy across the bipartition. So this is the answer which we are proposing here. So if this happens not only for a single bipartition of this considered quantum many-body state, but rather all possible bipartition of the state, then we are going to see that the quantum state obeys a generalized version of this area law feature for certain geometry. In other words, it's promised to get a path following which we can observe a bounded growth of quantum entanglement. Now, how to get the information about the path? So the information about the path is basically encoded in this J matrix. So if I have a quantum many-body state, and if I find that, okay, the formalism works well, then I am going to get a set of these Jij elements. And these Jij elements are going to tell us that what should be the path or what should be the orientation along which, if we look at the system, then we are going to recover an area law feature or bounded growth of entanglement entropy. So let me give you a quick example because I have mentioned maybe many technical things. So let's call our old friend this rainbow state. So if I apply this formalism for this rainbow state, then one can show that this ansatz holds exactly. So this link representation ansatz is satisfied exactly for this rainbow state. And once you apply this formalism, then the J matrix that you are going to get looks like this. So how to read this J matrix? So this J matrix tells you that all this white region are the zero, representing the zero value of this J, and the only non-zero value of this J are marked by this blue box. Okay. So this J matrix tells you that in order to recover this bounded growth of entanglement or an area law feature in the system, one need to see the system act like this, as if site 1 is interacting with 2, site 2 is interacting with n-1, and 3 is interacting with n-2, and so on. So you may remember that a few slides before we have already established these things, that this should be the right path to look at the system for which we can recover an area law feature. So this is also coming out from our formalism, and this is just a consistency check. But again, this is a very simple example, and to find this path, as I shown you before, that one does not need to apply our technique. But what would be the case if I consider a generic quantum many-body system? But before that, let me mention that due to this J matrix, here we are actually getting a very interesting thing. So which is following. So let me go back to this Hamiltonian, rainbow Hamiltonian that we have started with. So the physical system, so if we consider a physical system which is characterized by a geometry, then for the physical system, we can assign a intrinsic geometry that is actually coming out from the Hamiltonian of the system. So how to realize that? So consider this again, this rainbow Hamiltonian. So this is a free form Hamiltonian and has this nearest neighbor couplings. So one can see that this interaction in the Hamiltonian can be actually realized as a graph, where the vertices of the graphs are basically the lattice sites and the edges are basically the couplings. Okay, so this is a nearest neighbor model. So you can see the couplings are only with the nearest neighbor. So if I treat this as a matrix, then this will be the corresponding adjacency matrix. So this is basically the geometry that you can get from the Hamiltonian of the system. So this we call maybe the intrinsic geometry of the system. But this J matrix is also giving you another geometry related to the system, and that is coming out entirely from the distribution of the entanglement. Okay. So as I have shown that for this simple state, so the J that we are getting from this linked representation analysis looks like this. So you are getting a scope to compare the geometries. So in one case, the origin of the geometry is the Hamiltonian of the system. And the other case, the origin of this geometry is basically entirely the entanglement distribution of the system. But this is again, as I mentioned, this is a very simple example. So we need to look for the proper process to find out this geometrics for any generic quantum many-body system. So in that case, we need to rely on numerics. We have to basically solve this equation. So what do we have in our hands? So we have this entropies, which are known things. So for a given quantum many-body state, we have a large number of entropies. And using those entropies, we can compute this unknown Jij. Okay, so this Jij are basically they are n into n minus, for an n quantum state with n sites, the number of independent Jij will be n into n minus 1 by 2. So from now on, everything will be about computation of this Jij matrix and analyzing its property. But we also have to make sure that when we are relying on numerics, the numerics is faithful. Okay, because we can get a solution which may not be very much reliable. So for that, we have to basically construct a figure of merit, and that will decide whether this linear representation formalism is a good approximation or it's too much for the state. So here we are trying to do this in the following way. So what we are going to do is that, so once we apply the linear representation formalism, then we are going to get a set of entropies which are approximate. Okay, so we are going to get this Jij, and using this Jij, we can again construct the entanglement entropy across all possible bipartition of the system. Now remember, we have the actual entropies of the system as well. That means the entropy that you can compute if I give you a quantum system. So a deviation of the set of entropies which are actual and the set of entropies which are approximate can give us a hint that how good the approximation is. So in other words, we compute the difference between this exact entropies and the approximate entropies coming out from this formalism for all possible bipartition of the state. And then we take an average. So if this quantity is 0, which we observe, which one can show which, for the rainbow state, which is the case, or the states where we have are basically valence bond states, then we are going to say that this linked representation for that given quantum system is exact. But if it is non-zero, then of course we need to learn that this technique is not exact. But still we can work with that, provided the amount is pretty small than the actual entropies. So this epsilon guy is basically the figure of merit. If it is too large, then we have to say that the approximation does not hold at all. If it is non-zero, still small, then we can say, okay, the system does not obey this, satisfy this linked representation formalism, but the approximation is still not bad. So we have applied this technique to a large variety of physical systems. So that consisting of, for example, non-interacting systems, let's say free harmonic model like this. And we have tried to see that how this Jij behaves. So for example, here, if we have translation symmetry, then you can, instead of Jij, you can basically talk about Jr, where R is the distance between this sites I and j. And then you try to see that how the j is going to behave with the increase of this distance between the sites. And you also, as I mentioned, so you also have to take a look at how the deviation is happening, or how this figure of merit is behaving. You can see that depending on the parameter in the given system, this quantity epsilon has different behavior. So it's saying in some cases the system is very close to this link representation. In some cases it deviates a little more. So this is the things which we did not only for the non-interactive system, we also applied this for interacting system as well. For example, this Xx is Hamiltonian. And again, like as before, we tried to see how this J matrix behaves across different parameter regions of the quantum many-body systems. Apart from this, we also applied this technique to the cases where we have not only short-range interaction, but let's say interaction that decays polynomially with the size of the system. So these are the systems which are known to deviate from the conventional ideal of feature. So here also we try to see how this formalism works in this model. The cases are not only, or these examples are not only limited for spin Hall for harmonic system. So you also try to apply this thing for higher spin system. For example, in bilinear biquadratic Hamiltonian consisting of spin 1 system, and try to see how this behavior of, or how much, whether this J matrix gives us some information about different phases of the model. So, but yeah, I'm not presenting all the results here. It's just a summary. But the question is now that what would be the efficient method in computing this Gij? Because I mentioned that in numerics we have to compute this Gij, but if I apply the brute force way, then the number of entropies that we need to feed the system, that actually scales exponentially the size of the system. So the brute force method should not work beyond the moderate system size. So you need to find out a clever way to find this Gij. So we have tried to address these questions. So we have tried to take the advantages the system already has. For example, if we have translation invariance in the system, then we could show that this Gij elements, or JL, obeys a very nice recursion relation. So in order to obtain this JL, you don't need all the entropies of the quantum state. Rather, only few entropies would be enough. The cases where the system obeys an approximate or exact matrix product state representation, there we could able to show that this JL or this Jij decays polynomially with the size of the system, where this gamma is basically the second highest eigenvalue that comes when you construct the transfer matrix in this matrix product state formalism. Not only that, another technique which we found to be very efficient is the sampling technique. So here what we do is that instead of feeding the system the actual number of entropies, that means this of the order of 2 to the power -1, we feed the system relatively small number of entropies. So why this we expect this should work? So because in many cases you don't need to know the exact value of this Gij. Rather, a cartoon of this J matrix will be enough. So you may need to know that whether J12 is greater or lower than J13, like this. Okay. So in that case, we can obtain this cartoon of this J without, even with a very small number of input entropies. So this is the method called sampling. So where what we do is that we start with, let's say, some small number of entropies and then try to see how this J matrix is coming out. And if we are not satisfied with the result, then we increase the input, the size of the input set, and we keep on doing this until we get the desirable result. So this is basically the sampling technique, and we have seen that in all the results that I have mentioned here. If we try to get that using the sampling method, there you can get the qualitative picture very well. Okay, so this tells that the sampling method works very well. Now let me talk about the application. So some part of which I have already covered. So you remember from the discussion of the area law and the application of tensor network theory. So this is one long-term goal. So whether we can apply this knowledge of the bounded growth of entanglement in the improvement of this tensor network theory, mainly for two-dimension. Okay. Because in tensor network theory, so this is, as I mentioned, this is a numerical techniques, but in like as any numerical techniques, the tensor network theory also relies on the initial condition you are choosing. For example, if we let's say have a 1D system, so there are the two kind of tensor network theory. One is called MPS and one is called tree tensor network. So though they all both represent the same lattice structure, but in some cases, the one in this TTN or this tree tensor network may serve better than the others. For example, if we have long-range interaction in the system or the disorder in the system, then one can show that this should be the preferable initial point that one need to construct or consider in order to apply this tensor network theory. But how one can choose this numbering? So this what are this numbering? So this numberings are basically the position of the sites. Okay, that you also have to pre-decide before you start doing this optimization. Now there are many in literature. There are many ways people choose this. Sometime depending on the energy or the property from the Hamiltonian. But there are possibilities that one can also try to apply our technique and try to see or try to fix or try to get the information about this labeling using the entanglement distribution or this using this link representation formulation. So in this regard, I want to mention that one group from Japan has already done some work which based on this formalism. So they have acknowledged our work and where they have applied this not exactly our formalism, but at least they try to construct this initial tree tensor network by minimizing the bipartite entanglement across different parts. So it's good to know that it's been noticed, but it also tells us that we need to be faster and we need to apply this technique as soon as possible. Now, the other application. So the other application that we have shown is regarding the entanglement contour. So entanglement contour is basically a very interesting concept. So if you consider again a quantum many-body system or a quantum state, and if you try to compute the entanglement entropy, let's say, or try to see the entanglement across some bipartition, then entanglement contour tells that how much is the contribution of a given site I. Okay. So this is the notion of entanglement contour, and this has been introduced by Chen and Vidal long ago. But the formula they give is actually applicable only for free model. That means system without interaction. See, in our case, if you get back to this main unsuch or the link representation unsuch, then you can realize that this unsuch is basically giving a natural extension of this thing. So we can construct a similar to this entanglement contour. We can also consider something which by using this definition. So in this way, we can extend the applicability of entanglement contour not only for the free cases or the free models, but for the models where we have interaction. Because in our case, we don't care what is the origin of this quantum many-body system or what is how we are getting this GIJ, right? So in this way, the formalism extends the notion of quantum entanglement contour for the cases where we have interaction as well. So we try to verify this. So we try to compare that how good this entanglement contour coming out from our formalism is than this Vidal's case. So we have compared one such cases from pre models, and you can see those are numerically very close to each other. Now the other case, which I have not covered in details because otherwise I had to tell many things as introduction, is the application of this technique or this formalism in case of dynamics. So here we have a completely defined goal. So as you have understood that in the static case, there are many goals. One primary goal is to go to the areal of feature as close as possible. But when we apply this techniques in the dynamics, here the goal is something very different. So as we know that apart from the static property, another interesting thing to look at is that how the entanglement entropy is going to behave if we look at its time dynamics. Okay. So for that, what is the usual practice? So the usual practice is to start with an uncorrelated state and then evolve with under some Hamiltonian, of course, not the Hamiltonian of which it's an eigenstate. And if we do that, then the thing is that one needs to see that how the entanglement is going to behave. Okay, so we do it saturate or we do increase for a long time, so on. So people have found that if we consider the quantum state which are initially uncorrelated or has short range correlation, and if we quench that under some critical Hamiltonian, then the things are very well understood and well settled. So here the typical behavior is that up to certain time period, the entanglement entropy increases linearly with time. And then beyond this critical time, it saturates. Okay, so this is looks like similar to the area law feature that we just discussed. And this behavior is well explained using quasi-particle picture introduced by these people, Pascal Calabrese, John Curdy. So this quasi-particle picture tells you that when we quench a quantum system, then that generates a large amount of quasi-particles which are entangled, highly entangled with each other. And then they start moving across different parts of the system. And that's why different part of the system starts getting correlated or entangled. So this is very well understood and well settled formalism. But this formalism breaks down when you consider an initial state having long range entanglement or long range correlation. Okay, so then this quasi-particle picture breaks down. So in our case, in one of our very recent work, we tried to address this issue. So we have shown that using this J matrix, you can basically give a wave-like equation. And from there, by studying this evolution of this J, you can actually study the growth of entanglement entropy for the system. And in other words, how it is evolving with the time. So that helped us to give a compact form of the growth of entanglement entropy, not only for the short-range system, which I mentioned, which is well settled, but for the system where we have initially long-range correlation. So this is again this rainbow state. But we have also considered other kind of long-range state, for example, this bridge state. So you can see, like as the formula or the compact form of the entropy formula that we have for the short-range initial state, this J matrix formalism or this linked representation formalism helps us to get the similar compact formula of the entanglement entropy, even when we consider the initial state with a long-range entanglement. But yeah, I have not gone through in details about the formulation, and I'll be happy to talk about this some other day. Now, let me just mention very quickly about the current direction we are trying to explore using this JIJ matrix. So far I have introduced this JIJ matrix as some abstract quantity. Okay, but one can show that if we consider very small system size, that means n equals to 3, then this Jij basically remains proportional to the mutual information between the sites I and J. Okay, but this thing only happens for n equals to 3. So we are now trying to see that whether this kind of thing also holds for any general quantum state, that means for any general n. So can we relate to this Jij with some extension of the mutual information, or in-party mutual information. So this is the thing we are trying to work, and we are also trying to apply this technique in quantum information theoretic problems, for example, in discriminating or different classes of quantum states. And the other extension that we are currently doing is generalizing this notion by considering one more leg. So here we have introduced this as a kind of a 2D object. That means it connects the links I and J. But we can extend this formalism and try to consider this as a tensor. because this basically helps us to not only see the entanglement as a contribution coming as pair-wise contribution, but also the contribution which are coming as cluster between the step. That means the correlation that we cannot divide as a contribution from pair of sides. Okay, so this is a straightforward generalization from this, from the notion that we currently have. And then the aim would be to see that the cases where the current formalism does not hold or deviates, how good the things can be, or how much improvement we can make if we now consider, along with this Jij, we can now consider this Jij notion. Okay. So this is the main message I want to give. So let me give you a summary or the main message of today's discussion. So today I introduced a formalism that we call link representation formalism. So which try to see the entanglement between or entanglement across any bipartition of a given quantum many-variable system as contribution coming between the pair of sides. And this formalism helps us to generalize the notion of conventional area law, because this, if we find that we have an area link representation in the system, that ensures that we are going to get a path across which we are going to get a bounded growth of quantum entanglement. And I have tried to mention that why this bounded growth of entanglement is important, because that has one reason is, of course, that the applicability of this notion in numerical techniques, and this way one can access a system with large number of sites. So we have computed, so this, I have shown the examples where we have computed this J matrix for a wide variety of model, because we don't need any a priori choice of the models in which we can apply. So we can apply it in any model and try to see how good the approximation is. So I have mentioned the cases where we have interaction, we don't have interaction, where we have power law decay of correlation, as well as quantum system with higher spins. And the part which I have not covered in detail is the applicability of this formalism in case of dynamics. So where the goal is completely different. So here the goal is to extend the applicability of this quasi-particle picture in case where the initial state has long-range correlation. So this is the thing that I wanted to mention. And here are the collaborators from my past postdoctoral group with whom I am continuing this research in this direction. And thank you so much for your attention, and let me know if you have any question.
Thank you very much, Dr. Sudipto, for a very interesting talk. So are there any questions? Okay, if there are no questions, then we can thank the speaker once again for a very good talk.